All right. Hello, hello. Yes, start recording. Let's not accidentally press it. Let's see. Seaboard 1, Seaboard 2. Okay, I don't need to move too much. We're probably fine. Hello, welcome back to Lie Algebras. I have white chalk. Yes, I have a lot of white chalk, and I don't know, I'll use some of these. So today, the focus is, again, formalization of Lie algebras. But to do that, we're going to need some initial tools. I think most of us are like a second, third year. Okay, you might or might not have seen groups, so let's start there. The entire inspiration behind today's short talk is to talk about symmetries, because a lot of systems have symmetries, things that like don't change once you apply something to them. And so we want a language, almost some sort of system that we can talk about symmetries as practical and preferably maintains these symmetries. So let's start with the first concept of a group. Yes, you can see. So def a group, just call it G, equipped with a binary or I should say it's a set. Let's start with some set first. It's a set, a group, my bad, is a set G equipped with a binary operation. I don't know, let's call it like star for now. Star such that three things. Again, in the context of algebra, we always have some sort of group, some sort of collection of objects, some sort of set, a collection of objects, and we give it this binary operation that acts on only two elements of the set, satisfying the following properties. Number one, if we have, well, let's just call it associativity essentially. A star B star C is equal to A star B star C for all A, B, C inside of G. This is like how we would define for like a field example. Number two, there exists, not that, there exists E in G such that E is the identity. So if you, for all A star E is equal to E star A, it's just equal to A. Like it's just a classical identity. And the last, for all elements, there's some inverse. So there exists sort of like A to the -1 inside of G, such that A star A inverse is equal to its commutation, which is just the identity. So if you have some set and you equip it with some binary operation and it satisfies three things, congratulations, you have a group. The point of a group is if your set has some symmetry in it and you can like operate or you can use some binary operation and you'll get something that retains that symmetry. We will now, yes, go through a couple examples to demonstrate this sort of like property for groups. Oh, right.
So I'm not sure what you just said. That didn't quite sound right. The idea is more like a group is something, the elements of a group itself are the symmetries.
Okay, that's better. Yeah, that's better.
And then later, we're going to have something else. And we're going to come up with ways to act by the symmetries in the group on this something else. And so we'll see that later.
Great.
Go ahead.
Do I have anything? No, I guess. Can I do this here? Yes, I can do this. I have enough space. So, example. Am I using the wrong chalk? I'm indeed using the wrong chalk. Sorry. The general linear group, call it GLV, is...
So maybe don't start with this example. Can you start with one of the like simple
Sure.
triangle examples?
Simple triangle
Much
example.
better as a first.
All right, no, we're gonna start here later. Let's like drag another board out for now. Okay. Start with some intuition because this is a weird name. If you have, as I said, if you have some sort of triangle, and let's like label its points. Don't like assume by the number. Let's just label points so that we can call them something. The points don't really matter. If you look at all like combinations, like a three tuple of all points, then no matter the order, like you could create some other triangle that's like you rotate it. It's 1, 2, 3 here, but is it still like the same triangle? Yes, it's the same triangle. And so you could label this however you want, but whichever order you put this in, these are the same triangle. So these are the sort of like symmetries that like I want to talk about, where this ordering of the vertices is like symmetric-ish. So we will now consider the group for all like permutations of the edges of the triangle. And so, example, the dihedral group let's see if I have an exact name for this. Oh, let's call. So they call this D of 2n. With composition. What does this mean? If you have the subject we were talking about is a triangle, let's like generalize it, consider like an n-sided polygon. Then your n-sided polygon, as we talked about, you can sort of like rotate the edges and the polygon doesn't really change. It's still the same n-sided polygon. You could also like invert it, like flip it. And if you took some sort of like, for the triangle, you could take some sort of like axis here where if you flipped it, it doesn't really change either. These operations, like all these like rotations or like flips, inversions, did you find them? Reflections, sorry. The rotations and reflections are elements of the group. So G is composed. So the elements of G are actually like functions almost. They're functions that map certain edges to certain edges.
They are maps from the triangle back to the triangle.
Yes, and since they're functions, they're like maps. We can compose them. So the group binary operation is compositions of these maps.
So, I'd just say so. The dihedral group Dn is the set of symmetries of regular n polygon. Follow-up question: why is it 2n and not n? Why is it 2n and not?
In the book, it says 2n because you could, for any n-gon, you could rotate n like different degrees for the vertices. N vertices you can rotate n times to match the same shape. But then you could also pick n lines of reflection.
Oh, I see. So it's like counts the number of generators.
Yeah. Do you want n or 2n? It does not matter. Okay.
But like the reason why I want to mention is that like D2n is like standard notation people talk about this kind of thing.
Is a group. Should I write D2n? Like what it physically is?
You should say what it is.
Okay.
It's the group of symmetries of a triangle. So note that it's not just permutations of edges. Right? Because in principle, I could like permute the edges in such a way that kind of edges that were close together are no longer close together. This is the dihedral group is an honest symmetries of the polygon with like some rotation or reflection that keeps the polygon kind of in that. It doesn't permute like where the points are relative to each other.
Enough. Symmetry looks whack. I don't know. We'll leave that there. We have another example. Sorry. Try not to get your phone dirty. There we go. Aha. Our second example. is now purely based on permutations. So if you forget your notion of shape of like an n-sided gon, if you consider like a list, like a tuple, if you have A, like A, B, C, then the symmetric groups are permutations of this set. So you have ABC, you have BCA, and you have CAB. Right, hold on. My bad. Perhaps we should start with an illustration first. If you have some set, I don't know, like A, B, C, and you have the like A, B, C over here, then in some ways I could map each element to each element of itself. It's a bijective function. So I could map A to B, and then B to A, and then like C to C, for example. The claim is this sort of mapping are the elements of my set, and I can again compose these maps together. And what it would preserve is what's the symmetry here?
It's not the symmetry. So what is this set? This is just a set of all invertible maps on a set with from a set to a set.
Yeah. Okay.
So all the invertible maps from a finite set to itself.
Mm-hmm.
With n elements.
The symmetry groups.
Since the structure is very loose here, the symmetry would somehow be void.
Say that again?
For this example, since the structure is very loose, all permutations are acceptable.
Yeah.
Symmetry wouldn't be very, say.
Yeah, symmetry isn't maybe the best.
That's why this sort of confuses me.
But it's still called a symmetric group. I don't know. You know, the dihedral group of all symmetries of an n-sided polygon is a dihedral group.
That's
the group of all permutations is a symmetric group. I don't know. That's just
composition. I don't know what I'm writing.
The thing is that kind of this is something we won't discuss this, but in principle you can show that any finite group can be thought of as some subgroup of a symmetric group for some n. Yeah, that's not right. So if you understand all the subgroups of the symmetric group, then you kind of understand all the
Yes.
Whatever. I think that it's like all finite groups appear as automorphisms of a colored graph with finite colored graph.
probably, yeah, something like this.
Okay. Just a quick sanity check. The identity map here is just you map everything to itself, and things are invertible because I can clearly just go back. Same for here. The identity map for the dihedral group is just doing nothing, like leaving the polygon as is. And the invertible map is like I can always turn back. Like if I rotate clockwise, I can sort of like rotate not counterclockwise, but like the remaining way, and then I can always like return back. Same with reflections. And so now that we have a sort of okay understanding of what groups are, we want to like expand on this concept of just talking about symmetries. Now we want to talk about like continuous symmetries. So what if I didn't have an n-sided gon? What if I had like a circle and I like rotated it like this tiny little bit? We said finite, right? Well, that would no longer be finite. It'd be probably like it'd be infinite. You can't really count it. And so we want tools to be able to describe these like infinite sets of groups, if you will. Let's define. Oh, I haven't even done this yet. Right. 1, 2, over here.
You don't have to write on the same side. You can. I can move this a little bit. It's fine.
Careful. Yep. Thank you. Okay. I'll just start writing. So to do that, we need. So when we think about stuff that's like really big or infinite, we want to be able to change a small part, which makes us automatically think of like taking derivatives. To do that, we're simply just going to combine our notions of what a manifold is, and then what a group is, and we're going to call it a Lie group. But they don't really play nicely, so we want to add some sort of like compatibility conditions so that we can talk about both of them simultaneously and do like both techniques from manifolds and techniques from groups, if you will.
They do play nicely. It's just that we need compatibility axioms, so I don't just have two independent structures.
Right.
That don't sound good. And so the initial kind of motivation for this is that you can think of like rotations, say on a plane, right? Rotations on a plane are something that I can clearly parameterize in some simple way, like, well, just the angle, right? And that's, clearly that sounds like some kind of manifold, right? So, these symmetries where I can do like kind of, the idea is that I can apply a symmetry like a little bit. Like there's some notion of like twisting or turning something a little bit versus just some finite amount. If we want to describe that, we probably want to use a little bit.
That. And so the first condition we make is the binary operation of the group, called again star, is smooth. So you can take derivatives of it. And number two, was it right? The inversion operation. So it sends like a number of the some element of the group to its inverse is also smooth. So they call this like I. I from G to G is smooth.
And that's.
I'll just continue for now.
Instead of using I, you could like write minus -1 to the power of -1, like dot.
Star.
Star and then to the power of -1. I mean, sure, whatever.
Okay. I'll like draw some sort of like star around it.
Whatever the notation.
Oh, this is also smooth. This is just say if I have, I don't know, if I had a rotation. No, I'm not gonna give an example here. That's gonna be really bad. Do I talk about homomorphisms? Skip.
What about
Skip the definition. Skip.
I mean, yeah, you should.
Okay. So you can also, if you have like a manifold in the group, then we can, if they're two different like Lie groups, then perhaps you want to be able to go from one to the other. And to do that, there is like this like morphism. So let's define let G H be Lie groups. Let's just call this like 5. The map rho from G to H is homomorphic. Sorry. They can see if essentially compatibility here. So I didn't quite write the notes right.
What's the short answer?
The short answer?
What is a homomorphism in general?
Homomorphism. You can go between the two and you don't like lose information.
Sure, like you do lose information.
Do you?
You put it in
Ah, you do.
Point is, you have some structure here, you have the same structure, the same kind of structure there.
Mm-hmm.
So this map like preserves the structure.
Right. So in our case,
so what it's gonna do is just it's gonna preserve the group structure, it's gonna preserve the manifold.
Yep.
Well, not quite preserve the manifold. Play that.
Just call it like star, for example. This is for Y and H of Y. This is like the group part. You have the group structure, and
Whoa, hold on. Why do you have G and H?
they're different groups, so they have different group
What is
operations.
H of X?
H of X. Ah,
What is your map?
rho.
Rho.
Okay. No, wait.
So everywhere instead of G and H, you
Should be
go
rho.
with rho.
I'll be there. you have some G, wait, G of X then? No. I copied it wrong. All right. G to rho is homomorphism if you have some element of G. I don't know.
Yeah, if something was a product of two things, not comma,
Yeah.
something was a product of two things, then there it's still going to be a product of two things.
Call it like star then. Like this. Y.
No.
No. Rho.
Where is rho of x?
H.
Rho of x is an H, and where
Just
is
call it
x
X.
and y? X and y are in G.
G. Rho of. How would you transform?
Something that was a product in G should be a product in H.
Yeah, but it's not just X. Wait, let me think.
It's x times y
Yeah.
in G, so that in H it should be rho of x, what?
Ah, okay, that's my bad.
You've seen this a million times. Linear maps have this property.
Right. And differentiable. Okay. Don't use it much, but I guess FYI. So we've defined what a Lie group is. We can talk between Lie groups, and now we want to like give examples for what Lie groups are used. So let's drop this for now. Nope, you can still see here. So example. We want to look at the group of S1, so just a circle, which is written in the complexes. So this is Z. Given that, perhaps 2 dots here would be more appropriate. The norm of Z is just 1. Okay. So the claim is this is a Lie group. Let's like sanity check. What should be like the manifold that we're working here? This is S1. It's like a circle. Like what's an appropriate manifold?
The usual structure in R.
Yeah, just R. Why? Because it's some number, and using R, we can sort of like map every point uniquely to R. And so the underlying manifold is R, but we need to.
Sorry.
Yeah?
Whoa, what do you mean the manifold is R? Underlying manifold is not R. S1 itself is a manifold.
S1 is a manifold.
S1 itself is a
Really?
manifold.
Uh-oh.
So
Oh yeah, because it's on C.
Sorry.
Rip.
You're giving an example
Yep.
of what?
Hmm?
What is this an example of?
A Lie group?
A Lie group. Good. So you should specify what is the operation on it,
Ah.
and what is and how is it a manifold? Okay.
Under this is just multiplication. How do you call it? Like multiplication from complexes.
Yeah. So multiplication from the complex numbers. That's right.
Let's put a dot here.
Okay. And then what's the manifold structure of it?
Structure.
Remember, for a manifold,
So
what
R.
do I need to give it?
An atlas and a bunch of charts.
So give me at least one coordinate chart. You want to
It's not R.
parameterize
Yeah.
an open set of the circle
Mhm.
in some way.
Yeah.
Okay, how do you do it?
Like the example that I gave on like the last lecture. You look up from the north and you take the top half and project it onto a line.
Yes, but that's That's not a nice example. I want a nicer example. It's a circle. What's the most natural thing for a circle?
Natural thing for a circle.
Yes. What do you have? Like, just tell me where I am on the circle. What should
Like
you tell me?
angles? Polar?
The angle, yes. But in complex numbers, there's an even nicer way to write this down. With the exponential.
Ah. Okay, I lack knowledge there. Well, then what's the manifold? Just complexes? No, what's the manifold?
What do you mean? What's the This is
Complexes?
the manifold. S1 is the manifold. You have to give it a chart.
Yeah.
Right? The chart is going to go from where to where? Okay, well.
S1 to C. Or S1, no, to R. To R, sorry.
To R? Okay, maybe let's give a map that goes from R to S1, but it's still invertible.
Mhm.
What's a map that goes from R to S1? That uses angles.
A map. Sine? No.
Okay, sine doesn't give me a complex number. I need to
Yeah.
get a complex number. Help from the audience. We want to parameterize the circle, where we think the circle has complex numbers of unit 1. We want a chart going from R to S1, or like some open set of R to S1. And then in vertical way. Okay, give me one. Sir, I want a map.
R to
not
C?
from S1 to R. Let's go from R to S1, and then we can hopefully invert it. From some open set in R to S1. Give me any invertible map from some open set in R to S1. That's right. So theta to e to the I theta. Write that down.
Oops.
And if you take this from on the open set 0 to 2 pi, you cover
Theta.
almost everything except for one point.
From E to the I theta. Wait, what? Theta?
To e to the I theta. Yeah.
How is... Oh.
And remember that this is equal to cosine theta plus I sine theta.
No.
Plus I sine theta.
Plus? Yeah.
Okay. Maybe?
Mm-hmm.
And so this parameterizes the circle. Well, this parameterizes like everything except for the origin. If I go from 0 to 2 pi, and then I'm around.
There's an
the origin,
exclusion,
I
right?
can take another small parameter.
Mm-hmm.
So why is this the better chart to use than the stereographic projection? So on S1, I have a group structure where I can multiply two numbers. Do you agree?
You need some sort of compatibility between the two charts?
No. So far, we only have one chart.
Well, yeah, for this.
One chart.
But like if we pick the stereographic projection, you have like 2 points which are like blocked. You'd have to... No, wait, that's not a problem.
That's not a problem. That's fine. You always, like, the chart doesn't have to cover the whole manifold, it has to cover only part. And this chart also only covers everything except for, at least one point. You have to skip at least one point. Because otherwise you can look out or something. So, okay. Why is this a better chart to pick than the stereographic projection? What is nice about this chart? So, you have e to the I theta, where where I have great, on the Lie group I can multiply two numbers, and that's a group structure.
Mm-hmm.
Okay. On the reals, do I have a group structure?
With addition.
with addition. That's true.
or usual addition.
With the usual addition. What does this chart do? This chart, suppose I had theta and phi, right? This chart takes theta and phi and sends it to e to the I theta plus phi. But isn't that the same as e to the I theta times e to the I phi?
Yes.
So
Okay.
this choice of chart is actually like I already have a group homomorphism from R to S1,
Mhm.
and I just restrict it to an open set to make it invertible. The stereographic
Huh.
projection
Okay.
is not a group homomorphism. It doesn't do that nicely.
Okay.
This kind of thing is a group homomorphism and also a chart, so it's great. So you know 99% of the time use
I
this.
see.
The reason why the stereographic projection is nice is because it doesn't use cosine sine because
Mhm.
cosine sine are very complicated. But okay, whatever. No one cares.
Last part of this. Well, we wanted to check if it was a Lie group, and to do that, you just simply check if the binary operation of like multiplication and complexes is differentiable. I have enough space here and there, so I'll just give it to you.
You don't,
No,
you don't need to.
yeah, skip.
It's checking that multiplication is.
If you do a plus bi times c plus di, you get 4 terms. It's differentiable.
Well, you can show that it's you have to show it's differentiable in coordinate terms, right? That's what it means to be differentiable.
Okay, no,
So
no, we
it's not
we can
what
skip
you're
that.
saying.
We can skip that. That's more complicated than
I
usual.
mean, that's definitely an exercise you should do.
Right. 2.
Um,
How are we looking at time?
we're-
More than enough.
we have
We're good.
Okay, did you read the top 2 lines?
Mhm.
Yeah. Why do we want this? Is, for example, if you have rotation,
I'll continue.
I can rotate by like a very small bit. So, so in some sense, like my group of my symmetries are like continuous. So I should have a manifold.
Okay.
To describe that. And so, in fact, S1, you can agree, S1 actually will be precisely the group of rotations. Yes. S1 will also be precisely the group of rotations.
Oh, okay.
It will be the same group. Why? Because S1 is just
Should write a question on this.
point on the circle. And
Yeah,
the
yeah.
point on the circle defines how much you rotate by.
Okay, yeah, that makes sense.
Oh, the 6-sided star. So on a group is something with like a multiplication operation. And so he's just saying, okay, I have a map from G to H. G and H are different groups. They have different multiplication operations. So he denotes the one on G with a star and the one on H with the other kind of star to show that. And so once again, a homomorphism is something that preserves the structure. So that's just the standard thing of what a homomorphism is. But now we have a Lie group has a structure of a manifold and a group. So I have to preserve the structure of a group, which is like that condition with the stars. And then the structure of a manifold is R is different.
Wait, if this is smooth, is the inverse not or is this kind of the same?
Sorry, R is
Yes.
a homomorphism need not be invertible. Oh, the first part.
Yes. There's it's sufficient to show that if this is smooth, then this is also smooth.
Yeah. So 1 actually implies 2, but it's like.
There's a
little hard.
caveat. There's a caveat.
A little hard, so I don't want to show it. So might as well just do it.
It's yeah, in reals. Okay. Given that alpha is also in reals. Okay.
Sorry, this is not n by the matrices. This is 2 by 2 matrices.
My bad. Okay. So I think this is just a set of rotations, right? So they call this. Yep. The set of all rotations in reals is a Lie group. To show that, well, is there anything you want to say apart from like me just writing out like what they wrote on the book?
I think, do people agree that I can like compose 2 rotations, you have an inverse, and then if you, this already like tells you what the charts are essentially, right? The chart is alpha gets sent to this matrix, and then you have one chart from 0 to 2 pi, and then you can take another chart to include the origin or something.
Just take reals, but you have to exclude like 2 pi n because it's all like the 0 points.
Well, once again, if you have a chart, you want the chart to be invertible. So you want to.
Okay, I don't trust the book then. The book says things are weird. You could also say that since they both. No, actually, I'm not gonna say that. That's not good. Okay, right.
So people can agree that SO2 this is the same as S1 as a group, yes?
Okay, that's what I want to say.
And you may recall this from I don't know, tutorial 2 or something, 240, because remember we said the following. We said that if you have complex numbers, I can like A plus BI, I can instead look at the set of 2 by 2 matrices A, B minus B. Do you agree? And that's what this is, minus the part where this is like A, B minus B. That can be like norm not equal to 1. Right? This has like norm and substance equal to 1. But if I also allow to scale these, then I just get the complex number. Because if you just multiply this out, you get that the multiplication is the complex number multiplication, where the diagonal is the real part, the off diagonal.
No, I'm just gonna say it's a Lie group. Okay, so the torus, i.e., a donut, all donuts. Almost wrote the wrong word there. All donuts, you can chop off like a small section of it. They're all S1, it's like a little circle, and you can chop it all such that it's a Lie group under weird specific conditions. Just trust me. In the book, it says a Lie group under some quotient group. It's like specific some quotient group. It's built on like Rn over Rz or whatever. It confused me.
I think that's saying something a little bit different.
Okay.
It's just a Lie group.
What's the group operation? Like addition for your circles?
You just let's see. You just have this is what I have a bunch of like components, and then I just multiply everything component wise.
Okay.
This is the standard thing. If I have two groups G and H, then G product H is also a group where I just have pairs of elements, and I can multiply each entity.
But they have to have the same
No, they could have different operators.
So how do you define operation?
You have I'll just write this down quickly.
You want the mic?
No. If I have a group G with some operation star, and then I have some group H with some operation, I don't know, dot, okay, then I can look at the G cross H, where GH.
Oh, because you do each part.
Yeah, GH. I don't know how to do times. I don't know times G prime H prime. You can just the usual way to define it is G times G prime H dot H prime. So when people write something like this, they immediately.
It's like coordinate-wise addition or coordinate-wise multiplication.
There's technically, in principle, you could do this in some other clever ways, but this is a product of groups is defined to be a group with this other operation.
Perfect.
And so the torus is precisely that. And the torus, and I mean you can see how you get like the two torus, right? Is I have say one circle, do you agree? And then I have to have some other coordinate which is also a circle like this. Do you agree? But kind of at every point I have a circle. Yeah, so you can like
So it's cross.
you can get this into a donut.
Why donut's so complicated? Okay, a lot of definitions part. I just do it like here.
You
No.
can do whatever you want.
Bad planning. Yeah, it's not that much. I'll do it here, hopefully not cover it.
Turn around the.
We never do functions.
Can everybody see? No, they cannot see. We still cannot see. Oh, they can't see. Great. Okay. So we've defined Lie groups. We've given a couple examples. We're going to give some more standard examples, if you will. Ouch. Right. Okay. So let's call them classical groups. That's very big. I have enough space. Okay, we're going to define a couple of groups, and there's some terms that we need beforehand. Hopefully you can help me out with that. Right. We defined the, you weren't here, but the general linear group is just all invertible matrices.
I don't think you even defined it here. I stopped you. So just
Interesting. All right.
define it. We need
Define
to
it?
have the notation.
GL. I'll set this up beforehand. In the book, they do this for k is equal to reals and complexes. So all let's say this, not zero. So the general linear group for a certain field is just all invertible matrices for that field. Given such the special.
For the vector space.
Yeah, sorry, for the vector
the
space built on.
n-dimensional vector space of that is k
Okay.
to the n. Also, GL and k, sometimes people write like GL of V, where V is the vector space. It's the same idea. All invertible linear operators on the thing. Because also, whenever you write matrices, it's like, oh, I choose some basis, which is like,
Oh, that's why it's an N here, 'cause it's like the vector space.
n is the dimension. So the vector space here is k to the n. That's it, or r to the n, c to the n, whatever. The special linear
Group are all matrices inside of the general linear group. Oh, all right, thing.
So all the invertible matrices,
Mhm.
such that.
Help.
Okay. Stop.
The volume of
Yeah. Equal to
the volume of the set without A being applied.
yes.
And it goes to say like for all V, the list no
Or just for all
V1 for all V and N for all V.
Yeah,
in
and
R
K to the
K.
N. Okay. So people remember, hopefully from Math 240, what was the volume? The volume was something. So if I have an n-dimensional vector space, the volume is something that takes in n vectors and outputs a number. Okay, and it's something that has this like alternating property where if I swap two inputs, I get a minus n. And then one of the things, and it also has to be linear in each entry. Okay, so some alternating multilinear tensor. Good. And we showed in Math 240 that on a vector space, there's a unique such function. There's a unique such volume function up to some rescaling. Okay. So the volume, you can pick the volume to be any rescaling of the volume. It doesn't matter if A has this property for like one volume, then if you rescale it, I just multiply this equation by a number on both sides, nothing changes. Okay, so yeah, remember, the volume is some unique multilinear alternating function that takes in as many vectors as the dimension of it. And it's unique. There's a unique such function up to scale. So SLN is all the invertible linear transformations which preserve the
Volume. All right, we're going to introduce two more. They're the orthogonal group and the unitary group.
Yes. So no, so remember, volume, this is something that if I have a vector space, I immediately have some like notion, like some volume form on. That's fine. Right now, what we're going to is about, right, will be something about inner products. Right? So volume and inner products are not necessarily, not immediately.
That's too big.
So we'll introduce some groups that preserve this inner product structure.
There
These are
will
the
be
examples. This is
examples of like Lie groups, like very like classical or like very
this is
standard
already,
Lie groups.
This is already an example. Think of all the 2 by 2 invertible matrices. Okay. The volume is.
Also, I don't think we went over volume in 240.
Well, okay, I talked about it. The volume is, and no, you definitely did talk about volume.
I'm crazy.
You defined the
Determinant. We looked at determinant only for like
So you have
parallelogram.
So this is like if I have some matrix and I compute the determinant of it, then doing the determinant of A times that matrix is the same.
Oh wait, I get it.
Do you agree? Like the V1, Vn are like the columns of the matrix, and then you apply A to it, that just applies. That's right. So in fact, in a second, I think he'll rewrite everything and just write instead of volume of that is equal to volume of that, you'll get that the determinant of A is equal to 1, which is the exact same condition.
Okay, I'll put it. I was hesitating. I was hesitating. All right.
So yeah, volume V1 Vn is just the determinant of a matrix with entries V1 of Vn. But like the point is, like whenever you write it down as a matrix, that means you're choosing some basis, and then you have to show that your determinant is basis independent. But I don't need to show this. I just define it as something that's like multilinear alternating, and then I just show there's just only one thing that does this. That can do this, and so I don't worry about it.
Excellent. You have two versions that are saying if you're from all invertible matrices, there's this inner product such that applying A to both entries is equal to like not applying it.
And so this is with these usual inner products on Rn and Cn.
Is there something to be said about like the naming, like why like unitary? Yeah, like unitary, like unitary matrices. No, all right. Just pick.
I don't have something immediate.
They picked weird names.
to say about it.
So, what I put Rn?
Yeah, because
Cn.
it's
It's orthogonal versus like unitary is in the
O
complexes.
of N is all invertible matrices in Rn,
Mhm.
and then unitary is invertible matrices in Cn that preserve it.
The difference is here. Ah, my bad. Thank you.
No. Those, no. I mean, yes, and then, so at the very end you should have.
Do I not have?
Cn. Okay,
My bad. Okay. Now we've talked about the special linear group and this, and we want to find like the intersection of which belong to both worlds. Special, orthogonal.
Note that you also have a determinant, a notion of determinant on what? Yeah, on complex numbers as well.
Mhm.
Special unitary.
Okay. Do they have a name for this? Yes, they do. So SO of N.
Crazy. The
Inter.
orthogonal group is denoted by O, and the special orthogonal group is denoted by SO. Crazy. Yeah, exactly. And actually, the thing that arguably is the unitary group.
Mhm.
Yeah. The
And then we'll do
unitary
the same.
group is what will be very interesting when we put here in quantum mechanics. Why? Because in quantum mechanics we have some. The whole thing is about some, vector spaces over the complex numbers. So
The
you want to maybe look at some symmetries of that. But
okay. I'll put the tilde just to differentiate between union and intersection. Right. This is sort of like glossary. We have a bunch of these. In particular, we really want to analyze this one, and there is a claim.
which one do you want to analyze?
Oven.
Oh, Ben. Very sure.
It's the only one that we like talked about. You know. Okay.
Yeah.
That's what I was scared of. We have awkward input. Do we? We don't need this board, do we? I just can copy down the oven, the one in the back. It has like the thing we're talking about.
I feel like that's like self-explanatory at this point. Like, the group is a group.
It's gone. I'll keep that and I'll work on that one.
And rotate the.
Of course.
That's also more important. Probably no one on the Zoom. Or maybe there is.
We can check later.
Oh, I also completely forgot that this.
There's one participant. There's someone here. We need to be careful.
Is the Zoom in my headphones? The Zoom's probably in my headphones, so they can hear me really well, and Kevin like not so well.
I've said nothing useful so far. It's fine. I will just
More confidence.
put this over my head and we'll call it a day. Right, we're gonna delete this. And I've only given you definitions, so we want something sort of practical out of this glossary of different standard linear groups. Sorry, Lee groups. You're right, he's not. Wow.
I'm not presenting.
Oh. You showed up on camera though. Right. Where did I can't be losing this. Aha. I'll just call it what it is. Proposition.
So, yeah, the non-trivial thing now is, we said that these should be Lie groups, but like, why?
What was it?
Like, why? How do I
Interesting, I'm not
give
getting
this
this.
a manifold structure? This is not obvious at all. Like, if for rotations in R2, it's kind of obvious. Like, okay,
Mhm.
I can write down the matrix explicitly. For rotations in R3, that's already harder,
Mhm.
because then I can like rotate about many different axes. You still have like Euler coordinates for it, so you can use the coordinates explicitly. But okay, for like some 100-dimensional subspace, writing down the matrix explicitly is really not obvious. So what we want to do is we want to come up with some clever way to, so come up with a clever way to argue there's a manifold structure. How will we do this? Well, we will use results that we already know.
Okay.
C where? Yeah, SL and C. For SUM.
My bad. Okay. The proposition is O of n is some matrices that have a, I don't know, how would you call that? They do something special to the standard inner product. These are also the matrices that are symmetric.
Yes. And so
Or-
if you had SON, what would be additional condition B? It would be no. Sorry, SON, not US. What would the S add? It would just add that D.
It's one. Okay. To prove this, we're gonna have to take a little bit of a tangent. We should perhaps go back, and I'll use different chalk. I don't know. Yellow seems nice. We're missing a little bit of yellow today. Recall the implicit function theorem.
Sorry. Implicit function implicit function theorem, we're going to need to compute the dimension of ON as a manifold.
Should I still write it down?
Wait, hold on. What are you trying to prove right now? Trying to
This.
prove that?
This.
Okay,
Using
you
this.
You cannot use it to do that.
Ah.
Will not
Wait,
work.
what?
You use the implicit function theorem to
Oh,
argue
my
that
bad.
it's a manifold, and
I haven't even given you the clean the point there.
yeah. So let's do that.
It's called like. I'll just write this out. So compute the dimension of O of n.
Okay. So you're skipping a step.
Yes,
right?
sorry, that's my
So
bad.
you're skipping a step in the sense that there you wrote down that kind of definition for O of n.
Mhm.
There you wrote down that kind of definition for O of n. They're different things.
Yes.
Okay. It's clear that that set is a subset of that, right?
Mhm.
Because the transpose is the conjugate. Yeah, I just move it to the other side, I get one, and I get the same thing. And then I think using if you just started with that property,
Mhm.
you can show because it has to hold for all V and W. I think
Pick VV.
it holds for V and V.
Yeah.
And then you would like move it to the other side and then
A
subtract
transpose.
them or something, and you'll get.
It isn't.
No.
Yeah.
Yeah.
So this is like some standard thing where you manipulate it and you get the answer.
Perfect.
You do AB minus.
But it's a good thing to be able to do
Mhm.
because it's like you do it once and you're like, oh, it's the standard trick, and then someone asks you to explain it in like 2 years, and you're like, I don't remember.
It's gonna be me in
So
3
maybe
seconds.
you would
Right.
say 247, like 5 times.
Mhm.
You're like,
I guess this exercise, the inspiration for, or at least if we analyze this,
So, it's not just that we want to compute the dimension of ON.
Oh.
We want to show that ON is a manifold to begin with, right? We want to give it some manifold structure. So, that's fine. Okay, we wanted to show that it's a manifold and compute its dimension. We're not going to like show it's a manifold with all detail. We'll show some of the detail and then you can do the rest. But the dimension of the manifold is pretty important, right? Because that that tells me what kind of dimensional surface it is. That sounds useful. And it becomes useful later because it becomes useful later.
okay,
Okay, how are we gonna do?
I guess the way I thought about this is if you look up here, clearly, like there are less symmetric matrices than there are like all matrices. Also,
Sorry, symmetric or orthogonal?
it's not symmetric, orthogonal. What's orthogonal?
Wait, I think it's works out to be the same thing.
Oh, we showed that it's the same thing. I'm just gonna use this
Orthogonal
terminology.
matrices, symmetric matrices are the ones where like above the diagonal is the same as below the diagonal. That's not the same as orthogonal at all. No. There's many more symmetric matrices than there are orthogonal matrices.
Okay. Wait, what? Then how are these the same thing?
They're not the same thing. Sorry.
Okay.
Sorry. What's your? What are you talking about? What's your plan?
Like, why should I suddenly bring up implicit function theorem?
Okay.
Like, what's the inspiration?
So what's the inspiration? Let's write down the implicit function theorem, and we'll see what the inspiration is. To understand why we want to use implicit function theorem, we should know what the implicit function theorem is. And we had a day on it, right?
Yes.
When I asked Green to do a day on it, I was like, where am I going to use this? I didn't remember why it's important. So
Okay.
it is.
I don't need that much space for a drawing.
How many inverses are equal to transpose? You could, but it's not how many. It's not how many. Because you need the dimension of like how
differentiable?
many numbers do I need to like give it coordinates. And that's like unless you just find coordinates, it's hard. And And the implicit function theorem is going to help us find coordinates. So let's look at what the implicit function theorem is, and then we'll see why it's obvious. Okay, the implicit function theorem, there's like a related, more general theorem that one can prove and which we won't. But that's like it really helps you compute dimensions of like a lot of things. The idea is like, let's see the idea.
Okay. This part that I'm not sure about. The Jacobian matrix for D of F evaluated F adverse of P. Achieves full rank, yeah?
It's not
No,
the rank
the,
that has a rank n. I think.
the one that doesn't get shrunk.
Has rank n. I think that's right.
Yeah, because you go M to N,
Yeah.
and yes.
Rank n. No, rank
M.
n. It has rank n in some open neighborhood of P.
Oh.
No,
Ah.
some neighborhood of P. So it's df at P first of all.
Yes, evaluated.
df evaluated at P. It has to have full rank in an open neighborhood.
Not like this.
No, you're not evaluating. You're never going to evaluate df at F. Oh, so yeah, F inverse. Yeah,
F inverse.
Sorry, that's right. P is in the regular, right?
It's a
Sorry,
regular
F
value,
inverse,
whatever
F
that means.
inverse. That's right, yes.
Can you see? You can
Has-
see.
Has rank n in some open neighborhood of F inverse. Right, I remember, yeah, you need open neighborhood.
Yeah.
Otherwise, you could have something where it's like, at that point it has full rank, but then somehow immediately everywhere else it, or like, it doesn't. Like, you could have something weird happen. Actually, I don't think you could have something weird like that happen. But it's easier to assume it than to worry about proving some analysis fact. I don't want to do that. Assume every assumption you can to get a nice result from an assumption.
Okay. Ah, smooth. This is differentiable as well. And I run into a problem I thought I would not run into. I can just define it this way. Or
This is
yes.
This is whoa, X I think X is in Rn. Is that right? Yeah, because that's the part that
It's for some, right? For some X.
yeah. Actually it's not so this statement of the theorem is a bit incorrect
Mhm.
because when we write f of x g of x, this kind of implies like this full rank condition, like where it is in the matrix. I'm writing this included standard basis, and I need like a particular part of the matrix then to be full rank.
Mhm.
So this is true up to like some coordinate transformation of where how x and g of x go. But so this is roughly this is not quite the right statement.
F goes from M plus N, right?
F goes from R M plus N to R.
How is it? Oh wait, that's the
Yeah.
second.
So X is M, G is N.
Yeah.
So M plus N. Yeah, so the
This is the drawing, or this is the illustration.
the yeah.
The regular value is just saying the preimage of P is some like neighborhood like this, where if you take it, you always map to P.
So not quite. The claim is suppose I have a point
Mhm.
that gets mapped to P, and around this point, df is somehow like surjective always. Okay. Then locally around this point. So, so the function g is not from Rm to Rn. It's from some subset in Rm, like a small u in Rm.
Oh,
Right? So it's not. It doesn't give you the whole thing. Locally, there has to be some surface that is parameterized by m numbers, and that surface is precisely x comma g of x. That all gets sent into that point.
Can the people
So-
see?
What's the idea is remember the idea was very simple.
No, it's
If I have some smooth map from an m plus n dimensional thing into an n dimensional thing, right? That means I should be collapsing like an n dimensional thing in some sense. And so what the implicit function theorem says, there has to be some m dimensional surface that all gets sent to kind of one point. This makes. So how is this going to help us compute the dimension of some manifold? Okay. Suggestions from the crowd. How are we going to use the implicit function here to compute the dimension of a manifold? So what are we going to need to find? Yes.
maybe consider as a function from R into to satisfy some property that favors what's the word? The transport that inverse that should be 0 and inverse be negative. And then it cannot be linearly independent.
No, I want something even simpler. So we want to show that On is the manifold. Agree? So we want to find some way to parameterize O of n. Agree? In the implicit function theorem, what gets parameterized? What do we parameterize in the implicit function?
We should probably back it. Some point x inside of an m-dimensional like neighborhood.
Great. How do you parameterize the point? That doesn't make sense.
Wait, what?
What do we so in the implicit function theorem, you parameterize something. Can you erase the x?
8.
So what is it that you parameterize in this theorem?
If you take in a vector in matrix form, the first like m columns that are linearly independent.
No, that's not what I parameterize. What there's some surface here
Mhm.
which I give coordinates.
Yes.
According to this theorem.
Mhm.
What is this surface?
This green thing.
Okay, and what is that? What is it?
It's g of x. No,
It
wait.
is the inverse of p. Agree? Well, it's some part of the inverse
Okay.
of p that is sufficiently close to f inverse.
Mhm.
So that's great. So what do we want? What do we want On to be in this picture? On, we want to be the which color? The green,
Yes.
yes. So I want to come up with a map that I have On in some bigger space,
Mhm.
and I want to come up with a map that takes On and sends it into P. Okay? And sends it into some point such that it only sends On into this point. And then I want to make sure that this map, where this P is a regular value of this map, so it has some like rank condition. And then I know that in some choice of coordinates, I can then, like by the implicit function, I have the parameterization. Okay? And ideally, this map is going to do what? We don't know the dimension of On, so we don't know M.
Yeah.
But ideally, I'd like to know N, and then I'd like to know M plus N. So I want to know the dimension of the initial space and the dimension of the target space. And then I can subtract and figure out what the dimension of M is. Okay? So we want to find the map like this. Okay. And so this map, if you look at the definition, this map is staring you in the face. What should this map be? So I want to take an element I want to take
So,
something,
Oven?
and then which is probably a matrix, and then map it to something else. No, not quite. What do you have written right there?
GLN of K.
No. Look at what you have in the
Ah.
first line.
Yeah.
I want a map from somewhere to somewhere. It takes a matrix and outputs
Mhm.
something. There's a map already written there. No. There's no word determinant on that board. No, look. Only say things that are written on that board.
Bro.
On the very first line, look carefully. There's no derivatives, there's no determinants. There's a map. There's something that you can think of as a map. There's no inverse written on the first line. I mean, there's only so many letters written in the first line. So what about the transpose? You want to send A to what? Not just this transpose. What's written there?
Like this condition essentially.
Yes. So let's look at the map.
Sorry, that's bad calligraphy.
We look at the map, and so we're going to need to be careful about from where to where, but that's fine. Because from where to where, we need to make sure we know the dimensions.
No, we don't care about subsets.
All matrices into
How would you call this? All matrices to satisfy that.
all matrices into the symmetric. Just say symmetric. And I will say why symmetric matrix, why it's important that it's into the symmetric matrices.
Ouch.
I guess we have to know the dimension of that.
And yeah. So what's the map? I don't know, define it.
Thank you.
Okay. And what's the map? Phi takes a matrix A and outputs.
Another matrix.
Okay, what's the matrix?
The identity?
No. The identity map, that's useless.
Wait, yeah.
It takes a matrix and outputs one.
It's just like cutting out.
No.
No.
It's right there. You take a matrix A.
A times A transpose.
There we go. Thank you.
Mhm.
Yes. So
Or
it takes
it
A
sounds like
and
2
sends
months
it to
ago.
A times A transpose. Write that down.
Ah.
There we go. Phi of A is A times A transpose. Okay.
I remember this.
Okay. You can check that these matrices that A times A transpose is always a symmetric matrix.
Mhm.
Okay. Now, once again, we want to use. Why do we choose? There's two things about the trace. So first of all, why is it A times A transpose? Why is that the map? And second of all, why is it the symmetric matrix? Well, to use the implicit function here, we kind of wanted our whole thing to all be mapped into one single point, P. Do you agree? And for everything to be, we want our ON to be mapped into a single point. But by definition, ON is something that A times A transpose is the identity. Yes.
Yeah.
So the point is going to be the point P is going to be the identity matrix,
Mhm.
symmetric matrix. Okay. And so we're going to be wanting to use the implicit function here to look at the pre-image of the identity under this map and give it some coordinates. And that will give me precisely the orthogonal matrix. Okay. We're going to want to use the implicit function. Now, why am I mapping into the symmetric matrices and not maybe some other matrices, right? Because this could, this maps into the symmetric matrices, but this also maps into, all the matrices.
Yeah.
Why am I looking at particularly mapping into the symmetric matrices? What's the other condition about the implicit function theorem that I need? Smooth? Sure, I mean, of course that's smooth. It's always smooth. I need that df has rank n in some open neighborhood. So if I was mapping this into kind of all the matrices, then clearly that will not have full rank because it only maps kind of to a subset of the matrices. So I won't kind of be able to walk out from the symmetric matrices set into like other matrices. So the derivative will never be full rank that way. So, but I know that this definitely kind of should, it gives me kind of a bunch of symmetric matrices. So hopefully if I do symmetric matrices, I can show that, this derivative will indeed be full rank. And, okay, that's very good. So now maybe.
Assume
let's-
true. Assume true that D of
Yeah,
this
so let's-
has rank.
So for now, let's assume that it has rank, and then I'll prove it on the board after. So assume
Push.
that,
Writing here is like whack because like they can't see clearly.
Yeah,
They
that's
just move. Yeah, we like did not. This is
So for now, let's
getting
assume
erased.
that the theorem holds and compute the dimension, and claim that like if the theorem holds, how do we show that this is a manifold? And what? And then I'll actually show how to prove that it's full rank. And then we'll stop there. And then you can do like other SUN and these other things as an example. Also, I didn't actually post the readings for this week. I only
It's
kind of
true.
send them to him.
I wrote down the numbers in case you wanted to look
Yeah.
at the things.
He has the numbers of the book. We're no longer using mine.
You gave me 3 books, bro. I hate you.
We were initially going to use Fulton and Harris, but then I didn't quite like their discussion of Lie groups because it was like, I don't know.
The first
required-
sentence of like
it
definitions.
required you to read the rest of the textbook before getting to chapter 6. So instead, there's a third book which is Mathematical Gauge Theory by Hamilton, which has a pretty nice exposition of Lie groups in the first chapter. It's nice if you like still don't read half the chapter.
It's like definition 1.1.3.
But it's fun. Like if you know to only read, the right 10 lines in every page, it's a good book.
Maybe I'll like write it down later.
Okay.
Right. This is where I pull my iPad because I didn't finish my notes.
That's fine. So now what we want to do, we want to compute to do the theorem. What is the dimension of n by n matrices?
N squared.
Yeah, n squared. Right, and so once again, n by n matrices, they're a manifold, where the coordinates are literally the entries. Like it's just the same as Rn squared as a manifold. Or at least we give it this topology.
Right.
Okay. And now the question is, what's the dimension of the symmetric matrix? This is a question for the audience.
So the combinatorics is actually very annoying.
Sorry, no, not A times A transpose, dimension of the symmetric matrix.
Oh, wait, there's actually
It's not.
there's a
And diagonal. No, that's too large. In fact, we're
Because
n is whatever n is times n minus 1 is not.
it is,
No,
but you
not
cut the
quite.
diagonal already. So if you have n here, it starts at n minus 1 and it goes n minus 2. So
yeah, but then you would add them, not multiply them.
Oh, that's why. Okay, yeah.
Okay, so there's a simpler way. You need a simpler expression.
N squared
Uh-huh.
minus. My paper, I can do this. N plus n minus 1 plus n minus 2.
no, you're off. It's
No,
n.
no,
You start at
that's-
n minus 1.
That's the thing you're doing is the right thing. It will add up correctly, and you have. I mean, we'll just get that formula right now in a second anyway. How are we going to do this? There's a simpler way to account. So you could think of it as like, oh, I have n squared, almost. It's n almost, not quite. So one way to count it is I have n, then I have n minus 1, and then I add all of that. That's one way to do it. The other way you could do it like this, is I have kind of the diagonal, I have the bottom half, the top half. So total, I have n squared entries. Do you agree? Let's remove the diagonal, that's n squared minus n entries. Okay. But then to get a symmetric matrix, this has to be the same as this. So I just need to specify, say, the top half. So this means n squared minus n over 2. That's how many numbers I have in the top half. So write that down. N squared minus n over 2. But then this is what? What does this exclude? This excludes the middle row. So I have to add back plus n. Okay. And this
Simple
is
computation.
it's n squared plus n over 2.
Plus n? My bad.
Yeah, plus n over 2.
Wait.
Like they're all
Isn't this minus n?
It's minus n in the numerator. N squared minus n over 2 plus n.
Yeah, I was gonna
gives
say
you
this.
N squared plus n over 2.
Mhm.
Good. And so you can check that this is the same as adding up from 1 to n, because this is like n times n minus 1 over 2, which is like the famous Gauss formula where everyone says like, oh, like the teacher punished them or something. Yeah, exactly. Okay, so we have this dimension. Very cool. So now, assuming this theorem holds, what should be the dimension of ON? What should be this is a question for Kevin.
This minus this?
Yes, okay.
What? Why is it like?
That's right.
No. Isn't.
No, wait, shouldn't it just be that?
Yeah. No, but wait, implicit function. Don't sit on the desk. Owen is G, right? Like play matching puzzles. Isn't Owen just G here?
ON is what here?
Isn't Owen just like G from there?
ON is not. G is a map. How can
No, not Owen. Sorry, like phi. Phi whatever is G.
So phi is G. Then,
Yeah.
No, phi is not.
No, phi is not. Oh my God.
Phi is F.
So that's,
Maybe we should have called it F. Like assuming that the theorem holds, then we should be happy. Right? Assuming the theorem because we just have the dimension explicit. But there's still some caveats that one needs to talk about.
okay.
Squared. Sorry, why is there a minus there?
This?
Yes.
Minus.
Because you're subtracting this. Okay, and so what should this simplify to?
What? No. This is subtracting this entire thing. Yeah.
Yes, exactly.
So minus plus minus.
So what you have is put brackets around the whole fraction. Okay, good.
Ah, there we
Do you
go.
agree with this? This is how people write brackets. You always subtract the whole fraction.
Sure.
Do something between. Okay, and so this simplifies to. Yeah. We should double check what that we didn't make a mistake with the book.
The book. Where are the solutions?
It's in the somewhere. It's in the book. I don't know.
Perhaps you should check it out because I have not seen it yet.
AI overview.
AI will review. Should I do it?
Dimension
No.
of ON.
No, I don't.
It will give you the right answer. Like things like this are just like such well-known facts.
You know, hold on. Where's VS Code? I don't have it open. I don't want to do it.
Just Google dimension of ON. This should be correct, but I always make a minus sign error.
So we don't even need to know what G is.
Yes, we don't
G-
need to know what G is because the
No.
implicit functioning theorem just tells you like a G exists.
Oh,
It doesn't even explicitly tell you what G is.
I do not know that Owen is a sub. Isn't Owen a subset?
And yes, n squared minus n over 2, or better put.
N is a subset. It's is it a subset of the symmetric matrices? No, I don't think that implies.
Oh, wait, yeah.
That condition doesn't imply that you're.
Perhaps this is better.
Yes, this is correct.
Which is, it's just this. But like I took out an.
It's just a Gauss thing.
Yeah.
Yeah, exactly. And so now, okay, now you could do like a similar argument
Mhm.
for UN or SUN. Here you had a map from like
Can you see
some
both?
map that from like you just need to choose a different F. So particularly, I think for you need to be a bit more careful for the ones that include both that condition and the determinant. You're going to need something that maps to like symmetric matrices and the number. So you just do something that it takes a matrix, turns it to A times A transpose and the determinant. Yeah, like a cross. Yeah, cross. Exactly, and or at least I think that's how it would go. And then you just do a similar argument, and then you'd have slightly different dimensions. Okay. Yeah.
Wait, I'm like a little lost. So
Yeah.
we showed that the dimension of M is the dimension of the symmetric matrix, right? Which was
Sorry, you covered up the whole result. Can you like write it down in the corner?
The corner?
Yeah.
F and it goes to Rn, right? And then we have to subtract it from n squared. So we show that the m
So n
dimension
squared was m plus n.
Yeah. And then we show that the m dimension
Is
the dimension is that.
yeah.
How do we get from that to being that?
Yeah. So let's do a recap again. Implicit function theorem says what? If I have a map from m plus n to n with some nice condition about it, then if I have a nice point P, I look at the pre-image of that point. That will be some m-dimensional surface that has this parameterization x, g of x. So we also, what did we do? We defined some map that goes from Rn squared into Rn squared plus n over 2. Okay? We have not yet showed, but we will show that this like condition on the derivative is satisfied, meaning that the pre-image of the identity, so F inverse of identity, which is precisely On, that is something that can be locally parameterized using n minus 1 over 2 numbers.
Okay.
Right?
I see.
So,
but couldn't it be less than that if it were like, because the green box there is it's like a subset of the symmetric matrices, right?
it's a subset of no.
Sorry.
So it's a subset of all
the
matrices.
inverse of like.
It's the inverse of the identity.
Yeah. So like, how do I say this? Like, so P is the identity, right?
Mm-hmm.
So we know that like you take some symmetric matrix and if the symmetric matrix ends up being like A times A transpose is the identity. When you look at all the functions that go into that, it's some m dimension. Wouldn't that mean like for any P that it's always m dimensional? Like it's always that dimension?
Yes, for anything it will always be that. That's absolutely true. It's just that if you were trying to look at A times A transpose equal to something that's not the identity, that will not be a group under multiplication.
Sorry.
For something like this, because you'll have some like additional scaling that if you multiply those two matrices, you can get something back. So yeah, absolutely true. Why? Because the implicit function theorem is a theorem about manifolds. It doesn't know anything about how matrix multiplication works. This theorem just tells you how many coordinates do I need to parameterize a surface. And I need m coordinates, and so we got that. So, and how exactly this parameterization looks is not obvious. So one of the things that's like a bit not obvious about this theorem, so our initial motivation is we wanted to like argue that this is a manifold. And so what does this theorem say? So I'll just redraw the same, what colors to use?
Ivan, do you want?
What it doesn't. I speak loud enough. It doesn't matter. So, I'll draw it. I'll draw it like this. Okay, I have some map into some other space. Then I have some points. P here.
That's just the identity,
In our case, it's the
Yes.
identity, but could be any point. And so I can look at the pre-image of this point, which will be some. Okay, so this is looking at what? This theorem isn't really about a regular value, not just a regular value p. The claim is that if there's some p and there's some f inverse p, do you agree? Then the claim is that in some open neighborhood, okay, there exists some like surface here in this little open neighborhood that that this m-dimensional surface. This surface is parameterized by x comma g of x, where g of x is some function. Okay. This is in Rm. So this is some m-dimensional surface, right? Because I only need m coordinates because this is determined by the function. Okay. So I only kind of have this theorem only kind of tells me like what the local coordinate is around a particular point in the pre-image. Do you agree? If the derivative at this point is nice enough. Okay. This doesn't necessarily tell me everything I need to know about this being a manifold. Do you agree? Because for a manifold, I need because the whole set O of n is, this is only a small neighborhood of this point. The whole set O of n is like much larger. Do you agree? So what I need to do is this implicit function theorem gives me some way to get what? To get a coordinate chart going from Rm into kind of this Rm plus n. So this is kind of the inverse of a coordinate chart. Yeah. Oh, and there were some additional conditions on either like G being not G being unique, but some additional condition, I think, on G. That G was like particularly nice.
What's I said it? Sorry, I like forgot.
No,
I guess.
that's fine. I don't remember either. So this is what we won't do, but so this kind of gives me a coordinate chart around the point. I want to turn O of n into a manifold. So kind of what I want to do is I want to apply this implicit function theorem, get like some coordinate chart around like enough points so that I cover all of O of n. And then I want to show that they're like compatible in some way, right? So this x gets sent to x comma g of x. This should be the inverse of my coordinate chart. I need to show that, okay, first of all, this is honestly invertible, and that if I had some, some other coordinate chart for some other kind of surface here, which also kind of gets mapped to P by the same map, right? That kind of on this intersection, the coordinate charts have the like
Hausdorffness
transition maps.
Like Hausdorffness?
No, not Hausdorffness. I'm just trying. I have a chart here. I have a chart here. The charts have to be compatible.
Okay,
like the transition
I get it.
have to be smooth. And so this is something that you would need to show and think about. I don't want to do that right now. But do people see like what the additional work that needs to be done? Like this helps me define a chart around kind of every point of O of n, but then I need to show that all these charts are actually compatible with each other and give me an atlas and give me an actual manifold. Okay? People agree? So the implicit function theorem is only part of the way there, but it's the conceptually interesting part of it. This is like, okay, I need to, define my charts carefully and show what the inverse is. And yes, okay, I mean, this is obviously invertible, but whatever. Yes.
In our situation, what's G? Like there exists G, and the G is like.
There exists a G. We don't have there exists a G, and so that in our case, the G is the G that you get from this theorem if you this theorem doesn't like quite explicitly construct G. Well, kind of. And we will see this idea. Yeah, we'll see this idea quite soon, I think, with G. What's the idea? I have a manifold structure on all the matrices. Do you agree? And I have I have this O of n sits inside of the matrices.
Mm-hmm.
Do you agree? And I want to kind of figure out what is O of n kind of inside of these matrices. Okay, it's some submanifold. So what I want to do, and this is what we'll essentially do later, is I'm going to take, I'm going to find a point that is inside of O of n. And then, actually, what will be very easy is it will be very easy to compute the tangent vectors to O of n. What the tangent vectors are to that submanifold.
Okay.
And then I will say, okay, I know what the tangent vectors are. I have a starting point. So why not I flow along these tangent vectors and use that to map out what O of n is.
Is that like Lie algebra?
Yes, and that will be precisely the idea with the algebras, flows, all that kind of stuff. So we will have we will in some sense have an explicit way to find what the local coordinates are. Maybe not quite in this form, but we will have a way to do this later, not now.
Yeah.
Okay, yes.
Just general question for like higher level math. How many proofs are you expected to do once you're like third and fourth year that somehow like follow this kind of scheme? Because to me, this seems like a pretty far off idea unless you like use it every single day and you're really familiar with it. And you could just just pull it out. It's like, oh, hey, this fits really nicely. We can like map specific ideas. And
this is like a very important theorem that is just like, this appears everywhere.
Okay.
So this is something you will know.
Mm-hmm.
The only reason why this feels like a random thing to pull out is because you've only kind of seen it once in the context of like, we will need this later. But the general statement of the implicit function theorem is actually pretty simple. Well, pretty simple. Suppose I have a manifold M, and I have some other manifold N, okay? And I have a submanifold H inside here, okay? And I have some map F from M to N, and actually, yeah, F is smooth plus some other conditions of like this full. There's like some other full rank condition that you need somewhere.
Wait. Maybe we want to turn this around.
Smooth plus something else. Like you need an analog of this regular value condition. I mean, maybe like maybe like every point of H is a regular value for it or something like that. Then the claim is F inverse of H is a smooth manifold, smooth submanifold of M with dimension, a dimension of F inverse of H, dimension of M minus the dimension is equal to the dimension of N minus the dimension of H. So you have, this is the general kind of result for the implicit function theorem, meaning that kind of the preimage of this guy in here will be some other submanifold, and the point is that the difference in dimension between this and this should be the same as the difference in dimension between this and this. This is like the general result. We kind of proved it where H is a zero-dimensional manifold, a single point. Yeah, exactly. And so this is the more general result that you will see later.
Is that zero-dimensional or one-dimensional?
A line is one-dimensional.
Oh, yeah.
A point is zero-dimensional. And yeah, so this would be the general implicit function theorem. And with this, you can actually like compute the dimension of many, many things in precisely this way, right? Like I have some map, I have something that I want to know the dimension of. I map it into some other submanifold, which I know the dimension of that, in the space where I know the dimension of the whole space. And then, you know, I can, using this formula, I can figure out the dimension. That's precisely what we did here. Okay? Okay. So now let's actually prove this statement, and we'll be done. Oh, it's already 3 volts. Okay. Let's do this very quickly.
Do you want the microphone?
No, I'll just keep speaking.
You sit here then.
You don't have to like. I think from where you're sitting from, I can see the green thing. It's fine.
Mm-hmm.
So what do we want to do? We have this map. A sends to A times A transpose. Do you agree? And I want to show. So this is F. So F, and I want to show that DF at any matrix at a matrix in ON has full rank. So if I take so now let's take a particular point X, DF at X, where X is in ON is full rank. Do you agree? So how do I want, yes?
Made a small mistake. DF of F inverse of P, it should be like A inside of ON, no?
F F inverse.
Yeah,
of P.
we're putting it like in context.
F inverse of the identity.
Okay.
That's it. I want to show that this is full rank. Okay, let's see, how can I do this? So I want to show, okay, first of all, I need to show, I want to show that kind of the tangent space of the symmetric matrices is at the identity is fully covered in some sense. Okay. So let's see how we're going to do this. Okay, actually, I might not have this ready. That's crazy. I thought I did. Okay. So I want to find some. I have X, which is mine in ON. I want to add to it some matrix B, TB. Okay. I want to differentiate this with respect to T. So I'm like taking a derivative in the B direction. Okay. And I want to take this derivative at T equals 0. And I want to make sure that I can essentially get anything in the tangent space of the symmetric matrices. In the tangent space of the symmetric matrices, what is the tangent space of the symmetric matrices? It's just everything that's like, is it the symmetric matrices again? Something like this? I don't know, regardless. So we want to show that like I can always pick a B such that I get any tangent vector that I want after I get this derivative. So let's just compute this derivative, right? This is d dt at t equals 0 of what? Of a plus tb times a plus tb transpose, and I want to take this derivative at t equals 0. Do you agree? Okay, and then I'm going to say, like, show that I can pick b to be whatever I want. Okay, so if I take this derivative t equals 0, okay, the derivative is going to necessarily be a b transpose. Sorry, why is this a? This should be x. It's going to be x b transpose plus x transpose b. Do you agree? this is literally just like, you know, if I take a derivative with respect to t, t is 1, the derivative with respect to t is 1, the derivative of a constant is 0, t squared, derivative at t equals 0, 0. So just this times this plus this times this. And yeah. Okay. People see how I computed this derivative? It's with matrices, but it's the same thing. And now, essentially, I want to show that I can pick B to be whatever I want to get like anything I like. Okay. Okay, so now, you're right. The tangent space to the symmetric matrices are once again the symmetric matrices themselves. Why is this? Because the symmetric matrices are parameterized by, like, I have x1, whatever, and then here I have the same thing. So then, so this is, sorry, if I have like a, no, okay, let's call this y, y1, yn. But then here, if I have a, then here I also have a. So if I take a derivative with respect to a, the derivative with respect to a is some vector 1, 1. And then zeros everywhere else. Do you agree? So derivative, like tangent vectors of the symmetric matrices are symmetric matrices again. Do you agree with this? And so I want to show that I can always pick a B such that I get any symmetric matrix that I want. So let's pick B in the following way. Set B equal to x times C, like C, where C is an arbitrary matrix I want. Then if I set B to be equal to this, right, remember, tangent vectors to all matrices are just also all the matrices, right? Because then the matrices are like, I have all the entries. So if I take a derivative with any one entry, I can get whatever matrix I want. So then if I plug this in, I get what? I get x. I get x times C transpose. Wait, maybe this isn't quite what I want, but okay, let's double check. X times, maybe there's a particular condition that I want on C, but that's okay. X transpose times C. Okay. This, by assumption, is going to be what?
Just C?
No. X times X transpose. Well, yes, this whole thing is going to be just C, because X times X transpose is 1. Okay. And here, if I take the transpose, it swaps them. So I want here to also, I want to also get C transpose. Am I messing up? I am messing up, because here the order is, sorry, the order is, I wrote this derivative I computed wrong. It's x b transpose and bx transpose. Sorry, there we go, I had a mistake. It's like this. And then I will choose b to be cx. There we go, good. And so then, now it works. Yeah, because the order in which you multiply matrices matters. And then I get x times C dot x transpose plus CX x transpose. Okay, this is 1. Here, order flips, this becomes 1. So I get C transpose plus C, okay? But this is, I can always pick C to get any symmetric matrix that I want, C transpose plus C, right? C can be like the upper triangular, and then C transpose will be the lower triangular, and this will give me any symmetric matrix that I want. So I showed to you that at any point x, I can always differentiate in the right, in a certain direction, such that in the symmetric matrices, this gives me any direction in the symmetric matrices that I want. So I know that a derivative at x is full rank when once as you map in the symmetric matrices. Okay, do people kind of see? So like,
Yeah.
I'm mapping from here, from all matrices to the symmetric matrices, okay? And I just showed that kind of if I'm at the identity here, if I'm at something that maps to the identity here, at any point, so if I want to look at this direction, do you agree? Then there is a direction in here that I can walk along, such that after getting mapped by df, by f, going in this direction corresponds to going in any direction here that I want. So kind of walking around here, I can travel anywhere here locally. And that's what we just showed by, computing the derivative and showing that I can, for any direction here, I can pick a matrix here. Yeah.
The full rank parts is that we showed you can, like, CT plus C is always symmetric as well.
Yeah, so, yes. So I'm showing that I can pick an appropriate B to get, to make the derivative be any symmetric matrix that I want.
Yep.
So I picked B to get any symmetric matrix that I want.
Full rank. Okay.
Yeah, I can like pick C. This is always a symmetric matrix, and I can pick C to make this the right symmetric matrix that I want. Okay. All right. People agree?
Yeah.
So maybe as an exercise, find the dimension of UN or something like this. Okay. Sounds good.